I'm here to present our work, Learning a Robust Multi-Agent Driving Policy for Traffic Congestion Reduction. My name is Yulin Zhang. This work is collaborated with William Mackey, Jiaxun Cui, Daniel Riley, and Peter Storm. Traffic congestion has been a serious issue in our daily life. One form of congestion is stop-and-go waves. It happens in the merge scenario as shown in the video. When the human-driven vehicles approach the junction, they will stop to yield to the merging vehicles, and then accelerate to pass the junction. This stop-and-go pattern will propagate backward and significantly reduce traffic efficiency. Recently, a group of researchers showed that it is feasible to use a limited number of autonomous vehicles to reduce traffic congestion. Here is a video that demonstrates a successful driving policy for autonomous vehicles. The red ones are autonomous vehicles, and others are simulated human-driven vehicles. The autonomous vehicles reduce traffic congestion by creating appropriate headways in the traffic flow to accommodate the merging vehicles without hurting the overall traffic efficiency. But these driving policies are often trained and evaluated under the same traffic condition and do not generalize well. Here is an example. A policy is trained under inflow 1,650 vehicles per hour, and it is evaluated across different traffic inflows as shown in the x-axis. The y-axis denotes the outflow, but the performance drops quickly as we deviate from the training condition. Progress has been made to reduce traffic congestion. For example, effective congestion reduction driving policies are developed in both open and closed networks. They are both centralized and decentralized policies. There is also work that addresses the robustness of the policies. For example, researchers began to examine the handcraft policy under different AV penetration and driving aggressiveness. Robust policies are developed in single-lane closed-ring roads, but not in the double-lane case. Recent work develops a robust policy in the bottleneck scenario with a fixed road network geometry. In this paper, we develop a single-lane decentralized policy and demonstrates its robustness in different AV placement, traffic flow, and AV penetration. We further show that it can also reduce traffic congestion when deployed in roads with different merging ramps and roads with two lanes. To develop such a policy, we examine how the placement of vehicles affects the performance of the trained policy. There are two types of placements: even placement shown in the figure above, and random placement shown below. Next, we will train and evaluate the policies under these two conditions. We first evaluate them under random placement. In this figure, the red curves show the performance of the policies trained under random placement, and the blue curves show the performance of the policies trained under even placement. Unsurprisingly, when evaluated under random placement, the policies trained under random placement outperforms their alternatives trained under even placement in terms of both of their outflow and average speed. But when we evaluate these two types of policies under even placement, the policies trained under random placement still have better performance than their alternatives. We conjecture that this is similar to domain randomization, where the training data is more diverse in random placement. Then, we examine the policies trained under different AV penetration. The figure above has 10% vehicles to be autonomously driven, and the figure below has 30% autonomous vehicles. On one hand, more autonomous vehicles collect more observations during training. On the other hand, more autonomous vehicles means less human-driven vehicles, and those observations are less valuable in dealing with human-driven traffic. So when evaluating the policies under different AV penetration, we find that the policies trained under medium AV penetration balance well between the quantity and quality of the training data, and it outperforms others. Similarly, we examine the policies trained under different inflows. The picture here gives a sense of a low and a high inflow. we evaluate the policies across different inflows and observe that the policy trained under inflow 2,000 vehicles per hour, shown as the green curve, is better than the other policies trained with smaller inflows. We conjecture that the traffic patterns in the high inflow are more diverse than those from the lower inflows. As a consequence, the performance of the policies trained under high inflows is better than the performance of the policies trained under lower ones. Now we have constructed the best single line policy, which is trained under random placement, medium AV penetration, and high inflow. Next, we will deploy this policy in different road geometries and show its robustness in reducing traffic congestion. First, we examine the policy on roads with two merging ramps. These figures here describe different distances between these two merging ramps. In the figure below, the x-axis describes the distance of these two merging ramps. The y-axis describes the outflow. The blue curves show the performance of the policy evaluated with different AV penetrations, and the red curve shows the performance of the human-only traffic. When these two merging ramps are very close, there is spillback between these two junctions. As we increase their distance, this spillback effect decreases, and the performance increases. Overall, the results shows that the single-lane policy outperforms the human-only traffic, even when these two merging ramps are very close. Next, we deploy the single-lane policy on the right lane of the double-lane road, where the human-driven vehicles can change lanes to increase their own speed. Those lane-changing vehicles are considered as another source that could cause traffic congestion. Numerical results show that the deployed policy is still capable to reduce traffic congestion in this complicated scenario. As a summary, we have developed a single policy that is demonstrated to be robust in the vehicle placement, inflow, AV penetration, and road geometries. But there is more that can be done. For example, it is unclear to us whether there exists an effective left-hand policy. Additionally, all our simulated human vehicles share the same controller with the same aggressiveness level. Future work needs to address a heterogeneous human-driven traffic. There are definitely more road geometries we can consider, and we have not yet addressed the noise in the sensing and actuation delay, which are important to transfer policies from the simulation to the real world. If you are interested in this work, please check our paper. Thank you.